Okay, picture this. A massive, dark machine learning laboratory. Three giant gradient boosting engines are waking up, humming with power, all getting ready for the exact same training run. Now, every single one of these engines needs a learning rate to start, right? It's literally the master dial that decides how much each new tree changes the ensemble. Most libraries, well, they just hand you a factory default and send you on your way. But as we'll dive into in today's explainer, one of these engines actually hits the brakes. It stops, inspects the sheer scale of your training job, and calculates its own starting dial before a single tree is even built. Welcome to the learning rate nobody tuned.
Section 1. 3 engines, 1 mystery. If you've spent any time at all building gradient boosting models, you know that setting the learning rate is basically a rite of passage. But the way top libraries handle things when you just leave that parameter completely blank, it is wildly different. LightGBM, for instance, arrives with its dial basically superglued at 0.1. XGBoost's Tree Booster, same deal, firmly set to 0.3. But Catboost does something totally different. It calculates one context-sensitive constant rate. It doesn't just toss you a hard-coded number, it actually adjusts its starting point dynamically based on your setup. It's an absolutely fascinating mechanism, but honestly, it's pretty widely misunderstood.
Section 2. The optimization myth.
So when people hear that Catboost sets its own rate, they almost always jump to one very specific conclusion. They think, oh, it must be running some kind of crazy automatic hyperparameter optimization behind the scenes. We need to bust that myth right here, right now. It is absolutely crucial to understand what Catboost is not doing. It's not running cross-validation. It's not launching Bayesian optimization. It's not testing out some huge grid of candidate rates. It actually completely ignores your validation performance during this step. And no, it doesn't continuously adapt the rate dynamically after each tree is built. The result it spits out is a constant learning rate. It's not some adaptive schedule. Let me just be incredibly clear on this. If you leave that parameter unset, Catboost is not tuning your model. It's not magically searching for the perfect answer. What it's actually doing is just applying a carefully engineered empirical formula.
Section 3. Inside the source code.
Let's actually descend straight into Catboost's C++ source code to uncover the machinery and see exactly how it calculates this number. No magic, no black boxes. The formula is actually delightfully practical. First, it grabs n, that's your number of training rows. Second, it reads t, which is your requested boosting iterations or your tree budget. Third, it selects these empirical coefficient cartridges, let's just call them A, B, and C, based on your specific configuration. Like, are you running on a CPU or a GPU? Finally, it crunches the math, caps the absolute maximum possible output at exactly 0.5, and rounds it all cleanly to 6 decimal places. Now check this out. This is where it gets really interesting because it proves the first rule of the formula in action. Let's say we hold our requested trees perfectly constant at 1,000. When you feed the model 1,000 rows, you get a rate of about 0.04. But watch what happens as that data scales up to 1 million rows. The calculated learning rate smoothly climbs up to about 0.12. And the logic there is super solid, right? More data generally permits a larger, more confident step size. But look at the total push and pull when we do the exact reverse. This time, we're holding the training rows locked at 100,000. Watch what happens as your requested number of trees grows. If you only ask for 100 trees, Catboost just hits its cap and gives you a massive 0.5 rate. But if you ask for 10,000 trees, it violently pulls that learning rate down to a tiny 0.013. See, Catboost recognizes a fundamental truth that fixed defaults completely ignore. Your learning rate and your tree budget are inseparable. They are totally linked. A step size that works perfectly for 100 trees would be disastrously aggressive for 10,000 trees. We do have to be a little precise here, though. When people realize Catboost is looking at their data, they sometimes start claiming the rate is dataset dependent, kind of assuming the model is deeply analyzing their specific problem. But in this formula, dataset dependent solely means the size of the data, literally just the row count. The algorithm is completely blind to your number of features, your target variance, class imbalances, or your signal-to-noise ratio. It is absolutely not reasoning about the actual complexity of your dataset. And that really reveals the limit of the mechanism. Catboost is handing you a highly intelligent, fitted baseline based on scale and iterations, but it is not finding a guaranteed optimum. An intelligent default simply does not equal an automatic optimum. It's just a very, very good starting point. Also keep in mind, there's a catch. This formula doesn't trigger 100% of the time. It operates under some pretty specific conditions. If you manually set certain leaf estimation parameters or say L2 regularization, Catboost disables this dynamic calculation entirely. And then your unspecified rate just falls back to a hard-coded 0.03. Plus, simply supplying a validation set activates a flag called Use Best Model, which actually changes the entire coefficient table. Even just switching from CPU to GPU execution changes those cartridges we talked about, meaning your automatic learning rate can literally shift just depending on the hardware you're using. Crazy, right?
Section 4. The benchmark trap. Let's zoom back out to the macro level to see how this hidden machinery actually impacts your daily work, especially when it comes to testing models, because this is where things get a little spicy. Say you're setting up a race between LightGBM, XGBoost, and Catboost. Now, obviously, you can't compare the raw numbers directly. A 0.1 in LightGBM does not mathematically mean the same thing as a 0.1 in Catboost, because these algorithms build trees and handle regulation differently. But what you absolutely must compare is their default behavior. If you run a script with zero tuning, LightGBM and XGBoost are blindly starting off at 0.1 and 0.3. Catboost, on the other hand, is dynamically coupling its starting point to the exact size of the dataset you just handed it.
Which leaves us with a massive question for practitioners. Think about it. What did your out-of-the-box benchmark actually measure? Were you measuring pure algorithmic superiority, or were you simply measuring the quality of the library's default engineering? Look, defaults matter immensely. They affect your accuracy, your engineering time, your reproducibility. But comparing a fixed default against a dynamically calculated one, that is a fundamentally different question than a carefully tuned algorithmic comparison.
Section 5. Understand the machine. So now that we see the benchmark trap, how do we use this knowledge to actually elevate our daily forecasting and production work? The practical takeaways are pretty clear. Number 1, use Catboost's automatic rate exactly as it was intended, as a fantastic, robust baseline, but never as some flawless oracle. Number 2, because of the math we literally just reviewed, you must always validate your learning rate and your tree budget together. They're a package deal. Number 3, always utilize early stopping to prevent overfitting. And finally, if you're building forecasting models, always respect temporal dependencies. Because remember, that automatic formula is completely blind to time. This automatic learning rate is honestly just one small feature, but it carries a massive lesson. Catboost's real advantages, things like ordered boosting, categorical statistics, symmetric trees, and these incredible dynamic defaults, they live entirely beneath the surface. And that is exactly what the book Introduction to Catboost was written to uncover. It's about teaching you to actually understand the machine, not just how to call an API. Look, most resources out there, they just show you how to type import Catboost and basically call it a day. This book actually explains the hardcore engineering decisions that make Catboost fundamentally different from its peers. So if you're a practitioner wanting to truly master this machinery, I highly encourage you to check out the book at the link provided. Ultimately, the visible interface of modern machine learning libraries is incredibly simple, but the complex system beneath it, that deserves your full attention. So I'll leave you with this provocative final question as you head into your next modeling project. What other assumptions are secretly hiding inside your default parameters? Do not merely call fit. Understand what fit is actually doing.